oxidation and reduction. Okay. What do we got? Do we got any questions here? We're looking at oxidation state versus charge. The oxidation state applies to an atom. It is the balance of protons and electrons on a single atom. The charge is the balance of protons and electrons on something. What is that something? It can be anything. It could be an atom, in which case the oxidation state and the charge are the same, but different. Our oxidation state rules. This is just the shorthand modified version because this is what you need to know. Okay? You need to know your charges from your ionic compounds. Okay? This is why you did that with nomenclature. Oxygen will always be a -2 charge. And in the big part, the sum of the oxidation numbers equals the charge on your compound. Okay? That's huge. Okay? That you've actually already done. Okay? When did we see that formula before? And nomenclature. Balancing out a compound to make sure that our overall charge was 0, except instead of it saying oxidation state, what did it say? Charge. Why could we get away with saying charge there? Because we didn't want to confuse you with what it actually was, oxidation state. Right? It's the same, but different.
As far as balancing.
It's the same process, the same calculation. It's just how we apply that answer. Okay? So your unit can be a molecule, it can be a compound, it can be an atom, it can be a variety of different things. The oxidation state will always apply to a single atom, and it must always be calculated. Okay? Which gets us to our kind of examples. If we were looking for the charge for copper in that first one, that charge is always given to you. So for that first one, what is the charge on that copper? It is 0. There's nothing written in the upper right-hand corner at 0. The oxidation state for that same element must be solved for. And this is the part that I think people get confused on. So, well, isn't it 0? It doesn't mean you didn't solve for it. We solve for it using that formula. How many elements show up in that unit? 1. What is the oxidation state? I don't know. I got to solve for it. It's X. This must equal the overall charge, which I know to be 0. Solve for X. X is 0. The oxidation state and the charge end up being the same thing. This is why people get them confused. It's not just you. Okay? I went into this class to talk about, I think, redox one day, and one of the other lecturers walked out and mumbled something about charge and oxidation state being stupid to talk about because they're so confusing and they're crazy and they don't understand them. You should understand them. You're teaching it. Okay? And number 2, recognize that yes, they are easy to get confused, but they're applying different things. Your oxidation state is an atom, charge is the molecule. Okay? So if we were to go through and ask the question, what is the oxidation state for that lower right-hand corner, that compound being?
Sulfate.
Sulfate. What is the oxidation state for sulfate? You would tell me?
-2, but you'd have to solve. No?
You would tell me to go to hell. That's a stupid question. The oxidation state applies to an atom. Sulfate is not an atom. Asking that question is an irrelevant question. Okay? It makes absolutely no sense. The oxidation state applies to an atom. I cannot assign the oxidation state for a molecule. So fix the question. There's one way to fix it. What is the charge for sulfate? Now, Aspen, you're right. -2, because it's written in the upper right-hand corner. Fix the question, but this time it still needs to be oxidation state. What is the oxidation state for sulfur in sulfate? Now it's a valid question. How do we go through and solve that? How many sulfurs are there? Do I know the oxidation state? No, I got to solve for it. Plus 4 oxygens. Do I know its oxidation state? -2. How do we know that's -2? That's the one thing you have to have memorized on oxidation states. Oxygen is a -2. Right? This must equal -2. But doesn't it always equal 0? It equals 0 for a neutral compound. This is not a neutral compound. How do we know it's not neutral? It writes something other than 0 in the upper right-hand corner. That's how we know it's not neutral.
Can you keep that for a second?
Yep. Now that we've got the equation, we can go through and solve it. 1 times x is 4 times -2. It'd be -8, by the way, just to be nitpicky. How do I get the 8 to the other side? Add 8 to both sides, and I end up with the answer x equals 6. Nearly everybody will say x equals 6, and you will hear that I will almost never say x equals 6. You will hear me say x equals +6. I'm adding the sign. Just saying 6, well, is that a +6 or a -6? I'll always include that sign information because I'm trying to specify the balance of protons and electrons in the structure.
That's the oxidation state for silver.
That is the oxidation state for sulfur, okay, which had to be solved for. How to make sense? Is that a question? Yes?
What slide were those rules on for the oxidation?
37? That's actually a lie, because I deleted them from this PowerPoint and put them in the other one. Yeah. So if you're looking for the slides, try online lectures. See if it's in there. If it's not in there, I'll post it. So because it's not there, I can pause there if you want to take a picture of it. Okay. So there's all the answers circled out. Ta-da. So we could go through and repeat this for an equation. Remember, this is coming from the context of our balanced equations. So why are we bringing this in with balanced equations? Well, we go through and look at the equation above. We can look at what happened to the iodine. What changed? Went from a +5 to a 0 oxidation state. So what changed to the iodine? Okay. To be +5, it's missing 5 electrons. That's why it's a net positive value. To become 0, what had to happen? It had to gain those electrons. Okay, so we could reference its balance of electrons. In the course of the reaction, iodine gained electrons. What happened to the oxygen? Nothing. It started at -2, ended at -2. What happened to the carbon? Started at a +2, so it was missing electrons, and it went to a +4, which meant it's missing even more electrons. Okay? So in the course of running this reaction, we had a species gain electrons, and we had a species lose electrons. Okay? Where did it gain electrons from? Do you see electrons written into the equation? Okay. Electrons aren't written in there. They're not written in there because they are coming from the atom that lost electrons. Why don't we just write electrons in? What's wrong with that? How stable are electrons? Insanely unstable. That's why we don't stick forks in electrical outlets. Okay? That allows all the electrons to come pouring out and run through our body, and that's not a happy feeling. Okay? Electrons are highly unstable. We can't show them in a fully correct and balanced equation because they're that unstable. Okay? So they have to be balanced out somehow, which gets back to balancing equations. Okay? But we need to have a condition under which we decide now I should look to balance the electrons. Because hopefully we don't have to do this every single time. Doesn't that kind of suck? Every single reaction, you got to check the electrons. Right? Everybody's like, that's not that big of a deal. Okay. That means every single question on the exam, I'll make sure there's an extra one that says, what's the balance of electrons? No, it's okay?
It's a big deal.
Okay, it's a big deal. I agree. Okay? So we don't want to have to calculate every single time. We want to acknowledge it. Find reactions that allow this to happen. Okay? If we're going to try and find something, it might be helpful to name it. Okay? If I said, watch out for that grizzly bear barreling through the door, you'd all kind of freak out about the grizzly bear. What if I just said, watch out for that, whatever. Okay? We need a little bit more context of what's dangerous about it. So what do we need? How about a name? I want to be able to name this and identify it. I could just call it the gain electrons, loss electrons reaction. Or not. Yeah, that's kind of a dumb name. Okay? So what do we come up with? Oxidation and reduction. Oxidation, where's that term coming from? Oxidation was the loss of electrons. What species lost electrons? Carbon. What happened to carbon in the course of this reaction? Lost 2 electrons. Yes, look at the reaction, just the reaction itself. What happened to carbon? Left side versus the right side, what changed? Nothing changed the carbon? Okay, so I'm still hearing the, hey, go away. I didn't ask you to do that. Still hearing this gain and loss of electrons, so knock that off. Can't tell me you gained and lost electrons. What happened to the carbon? Say that again? I don't know who said that. Carbon is bound to 1 oxygen on the reactant side, and on the product side it is 2 oxygens. It has increased the bonds to oxygen. Hence it was oxidized. That's the word oxidation. We've increased the amount of bonds to oxygen. There's more oxygen, so it was oxidized. That's where that word is coming from. Okay. What about the reduction? Well, which species was reduced? Well, iodine. Well, what happened to iodine in the course of the reaction? It lost oxygens. The amount of oxygens was reduced. Reduction. There it is. Okay. The other thing we can do with the reduced that can help us out. To go from a +5 to a 0, what did I do to the number? I reduced it. Hey, cool, look at that. Okay. Reduction comes back to either using oxygen or using the oxidation states as our references. Okay. Does that mean our reduction and oxidation reactions will always involve oxygen? No. Okay. Why do we name them after oxygen? Because that's where they were first discovered. Okay. So we need to be able to identify our redox reactions or our reduction and oxidation reactions by looking at oxidation states. If our oxidation state changes, we're doing a redox reaction. That snowballs us into a whole other system of complex calculations that we've got to worry about. Okay? So we need to be able to label a reaction as reduction or oxidation. To do that, we have to remember that oxidation is loss of electrons. Okay? Or rather, loss of electrons is oxidation. Okay? So it might be helpful to come up with a mnemonic device. Loss begins with L. Electrons. Oxidation. Hey, that's creative. Gain. Electrons. Reduction. Leo happens to be the Greek or Italian, whatever it is, for lion. What do lions do? Grr, there we go. Perfect. Everything's now set up in a nice little mnemonic device. Leo the lion says grr. Okay? For those of you who think that is stupid, you will still, a reaction comes out and you ask me, you will probably see me mutter under my breath, ew, loss, electrons, oxidation. Oh, that one's oxidation. Okay? I will still do that. Okay? Bad memory. Got to say something. Okay? I apparently am one of the few faculty on this campus that use that. And for some reason, the rest of the faculty are anti-environment because the one they use is oil rig. Yeah, that's not nice. Okay? Why is this one even more obnoxious? O for oxidation. I for who uses a 2-letter thing as a letter in your acronym? That's just dumb. Okay, but let's just accept that. Oxidation is loss. Loss of what? Jumped to the pool, lost my pants. Does that mean I was oxidized? No. What happened? It has to be electrons. Oh, so the next letter is not E. Okay? This is stupid. No strong opinions whatsoever about this. Okay? Leo says Gur. Write oil rig on your exam. I dare you. Okay? As long as you remember it, it doesn't matter. But you have to tie back that the loss of electrons through the course of a reaction is oxidation. The gain of electrons is reduction. So you have to be able to identify your oxidation states for every single reaction's too vague. Equation's too vague. The oxidation state you have to determine for every single atom. Every single one. What was that about? Every single atom. Okay?
I hate to ask you this, but can you show how carbon becomes like +4 in the product side? Is it like showing the math?
Yes. We all good on what's up there, though? Okay, so here's what we'll do. Because all of that is just nonsense. We don't need any of that, right? So, oxidation state for carbon. Well, we're trying to solve for it, right? So, where do we start? The number of carbons. How many carbons are there? What's the oxidation state? Plus? 2 oxygens. What's the oxidation state of oxygen? This has to equal? Why are you saying 0? I don't accept 0.
Not 0.
The overall charge. What is the overall charge on this molecule? That is now 0. Upper right-hand corner. I didn't say you were wrong. I just said I didn't accept it. Okay. Overall charge. Stick with the overall charge. 1 times x? X. Plus 2 times minus 2. Must equal. Must equal. Must equal. 0. Sorry, that was your fault. X equals minus, or x minus 4 equals 0. How do I get the 4 to the other side? Add 4 to both sides, and I end up with x equals 4.
So when you solve, you just ignore like the coefficient in the front?
Yes. Why can we ignore the coefficient?
It applies to both atoms.
Oh, that was not supposed to happen. Yes, the coefficient applies to both atoms. So let's go through and scale that. What if we hadn't done that? I'm not erasing everything again. What if we applied that 5 all the way through? We have how many carbons? Times x plus how many oxygens? 10. It's not 7. The 5 multiplies through.
Okay.
10 times negative 2 equals our overall charge. Good catch. Which is 0. 5 times x minus 20 equals 0. I get 5x equals positive 20. Divide both sides by 5, and I end up with x equals positive 4. Okay? I can bring the coefficient in. The issue with bringing the coefficient in, you better make sure that you multiply it all the way through. Okay? That's usually mistake number 1 that students go through. Well, that's usually the mistake students make. Okay? The next part of it is you're now doing more calculations. What happens when you do more work? More opportunity to get something wrong. Yes, Tyler.
Will there ever be a situation in which like carbon is in 2 compounds in the result?
Can an element show up in multiple different places on both sides of the equation? Yes. Would I expect you to determine the oxidation state for the element on both sides of the equation? You can. Yeah, absolutely. Okay. What you have to acknowledge, though, is then when did it change, when did it not change? What you'll end up finding in those cases is that in one case, it won't have changed. In the other case, it will have changed. Okay.
So like if the results of our carbon dioxide and carbon monoxide,
Yes.
carbon would have two different oxidations.
Two different oxidation states, where in one case it did nothing, the other case it did something. Typically that happens with oxygen. Okay, so we're good? Okay. As if that was not enough, anybody recognize that, right?
Yes.
Yeah, good. Okay, we get a little spy versus spy thing here. What's going on here? What happens if instead of looking at the species that was oxidized or the species that was reduced, I ask for the oxidizing agent? Well, as an agent, what is it doing? It is causing something else to be oxidized. Because it's the agent doing it. It's causing that one to be oxidized. Well, something else is oxidized. What happened to it? It was reduced. Everybody catch where that goes sideways real fast? Okay. Let's take a look at the reducing agent. If I am a reducing agent, I am causing something else to be reduced. If something else is reduced, what happened to me?
You gain or not.
So go easy first. Something else was reduced. So remember, these are partnered. If I have a reduction, I have an oxidation. If I cause something else to be reduced, what happened to me? I must be oxidized, which means I lost electrons. Leo. Okay. So we get opposite terms coming out of that, and we have to be kind of careful with that labeling. The oxidizing agent and the reducing agents will both reference the molecule, okay, that did the action. If we asked for the element that was oxidized, I don't need to specify the molecule because I say element. All I got to do is specify the element that did it. Okay? The agents tend to apply to the molecule or the species that we added into the solution. Oxidation and reduction typically refers to the element that did the changing, not the molecule where that element was sourced. That's why we have the two different terms. So if you see ing, not a bad idea to just kind of panic and skip it. Okay? Or the instant you see ing, which is what I do, ing, oxidizing agent, I want the one that was reduced. Reduced meant gain of electrons. I can now go back to my equation and find the element that gained electrons. Whatever compound contained that element, I now have the oxidizing agent. Okay? Writing that work down means you aren't doing it in your head. For those of you who don't think doing things in your head is a scary thing, if all of a sudden the lights turned off in here, do you think it would just be like a normal class period? Everything just went dark. You saw nothing. Just be like, oh yeah, whatever. I'm used to things just going black. Okay? You'd all probably panic a little bit. Why? Because you're scared of the dark. Why are you scared of the dark?
You can't see.
The only access you have is what is in your head. You are scared of your brain. Get out of your brain. Write it down. Okay? Write that information on the test. You will no longer be afraid of the test. Hopefully. Okay? The instant you keep all of that locked up in your brain, you will confuse yourself and you will get it wrong. Write it down. Okay? With the ing is typically the only way that I test it, but every so often you'll also see reference to the oxidant and the reductant. So if you see ing or ant, it's a good idea to slow down and make sure you're looking at your definition appropriately. Okay? Because they're both referring to this whole spy versus spy thing. Kind of makes sense? Okay. With that, identify the oxidation states. First one should have been really straightforward. The oxidation state is the same thing as the charge. Our unit is just one of those. So 1 times, I don't know what the oxidation state is, equals the overall charge on that unit. X equals whatever that charge is. Okay? Which is what Brooke was attempting to write there. She just didn't write it down. But I understood what you were trying to do with it. Okay, with the first one. James went through and added a little bit more information to make sure that we could tell that that was the oxidation state. He just circled the charges across the top. that works out nicely. Because there's only one element in those, the charge is the same as the oxidation state. Okay. We move to the next one down. Okay. What is the charge in the first unit? There is no charge. It's 0, which then means the oxidation state is 0. It solves trivially out of it. Okay, so we've got the work for those two written up on the boards. Slightly different in both cases. I do want to call some mild attention to what Brooke gave us over here. I'm just going to erase everything. She's written the oxidation states up above, which isn't a horrible idea. The issue that I have with that is that if you move into another class, if you start writing things above, they might start to interpret that you're saying those atoms are charged, which they aren't. They're in a compound, so it can be a bit dicey to put that information up there. Just be aware of that. Okay. So the nitrogen was then a +5. I agree with that, and then I'm seeing a -6. The +5 is what?
Nitrogen.
The nitrogen oxidation state. What is the -6?
Is 3 oxygen.
The charge from 3 oxygens. So you're specifying different information in the same location. That can be confusing. Okay? So what should get written above that oxygen would not be a -6, but instead -2, because what you were trying to include is the oxidation state.
Of a single one.
Of a single one. Yep. And it will always be a single atom. If we have multiple atoms, they now have a charge contribution to the overall molecule because there's multiple things. Okay? But it's always a single atom.
How did she get -2 then? Or how did you get -2?
How do you get -2? The oxidation state for oxygen is always -2. You are required to have that memorized.
Is there any other atoms that we have to have memorized for oxidation?
Let's take a look at the bottom example. Oxidation state for the first unit. +2, that should be a straightforward one. What is the oxidation state for our elements in the next one? Oxygen's a -2. How'd you get sodium being a +1? Because this is going to Cheyenne's question.
You can find the charge on the periodic table.
I don't accept that because the charge is different than our oxidation state. You're going to the right idea.
You know, there's one of sodium.
What is sodium? Give me what sodium is. A metal. What is oxygen? What kind of bond are we getting somewhere in here? An ionic bond. If we have an ionic bond, we can split that into the ions. What is the charge on the ion of sodium? +1. The charge on the ion of the complex ion, which you haven't seen, don't worry, bismuthate, has to be -1. Now we have a new unit. That new unit is Na+. What is the oxidation state now on that unit? Now it's a +1. Okay? So what you did was do some kind of mental calculations recognizing that it's an ionic bond. That was one of our rules. If we have an ionic bond, you can split it into the ions. We now have charges that you may or may not be responsible for. If you are responsible for them, you got to do it. Okay? If you aren't responsible for them, then what do? Raise your hand and be like, jerk, fix this. Or I'll be like, no, actually, haha, trick question, you should have known that. Or look at all your answer choices. Maybe one of the answer choices says impossible to determine. Okay? Make sense? So that should answer your question. We got other questions on this.
Wait, so you have to separate the two?
You would have to separate those two because you need to be able to determine the oxidation state on the sodium. The only way you get the sodium and the bismuth, neither of which we can solve for directly because they're both unknowns. When we split it into the ions, then I have Na+, I can now solve for the oxidation state of the sodium. Okay? When I split it into BiO3-, I can now solve for the oxidation state of the bismuth. Okay? How did I know it was BiO3- and not a different charge? Sodium is always a +1 charge, which means when I put it into an ionic compound, the bismuthate must balance it out. It has to be a -1. Goes back to the balancing of charges, which you did in nomenclature. stacks very fast. Questions? Okay. Lie. What else could we ask about it? What changed? Let's go to the first equation. Sorry, I need to figure out some color coding. Okay. What changed to the tin in the course of the reaction? Went from a +2 to a +4, so it lost electrons. So we're looking here, that lost electrons. What does it mean if I lost electrons? I was oxidized. What happened to the iron? Well, if the tin lost electrons, the iron had better gain electrons. What's going to happen to its oxidation state? It should be reduced. We go from a +3 to a +2. Did it get reduced? Yeah. So gain electrons, reduced. What was the oxidizing agent? So the oxidizing means I need to think of the opposite thing. So instead of the oxidized one, I need the reduced one. The reduced one gained electrons, which was more specific. Which species was reduced? Iron +3. Iron +2 was the result of having been reduced. It did not itself get reduced. Your agents will always be reactants. They have to be. All right? So our iron +3 is now our, what did we say, oxidizing agent. That says oxidizing, an agent. What was the reductant? Oh, stupid ant. Reductant, that means the one that was oxidized. The species that was oxidized lost electrons. The one that lost electrons was tin +2. So tin +2 is the reductant. Okay. Notice in all of this, I can ask at any stage, what was the reductant for this equation? What do you have to do? Reductant means oxidized, which means loss of electrons. Now that you know it was loss of electrons, you go through and assign oxidation states for every single element, and you find the element that lost electrons. You have to stepwise through it. For those of you who can do it in your head, if you do it consistently, great for you. If you do it inconsistently, write it down. Okay? It was me laughing at you, by the way. Okay, make sense? Let's take a look at the next one down because we have the answers up on the board and I don't want to solve all the other ones. Our copper was a 0, 0 plus. Was a 0? Sorry. Nothing to do with color coding or anything. What happened to go from copper to copper +2? It lost electrons. Loss of electrons was oxidation or oxidized. Okay. That would be known as the reductant, just because you added that. Okay. What happened to the oxygen? Nothing happened to the oxygen, so I don't care. What happened to the nitrogen? It went from, what was our charge? We said a +5 to +4. That number was reduced. So we lost, we gained electrons, which means it was reduced. Okay. What was our oxidant? There we go, good answer, or almost good answer. Our oxidant was NO3 minus, we need to specify that charge, also known as nitrate. And that was then our oxidant. Okay. You should be able to do the exact same thing with the last one. And those of you that printed out the slides had this whole quiz thing even easier because I'm pretty sure the slides actually gave you all that information. So you could have just, oh, here's a slide. I'm just going to write up the information Mike already gave me. Oh, printing the slides could be useful. Maybe he was onto something there. How do we balance these? Take a look at this reaction. Is it balanced? No. How would you balance it? 2 in front of the H plus, right? Is it balanced now?
No. No.
How many zincs? 1 and 1. Why are you saying 2? Where's this 2? That's your charge. It's not a coefficient. It's not a subscript. We aren't counting zinc atoms. We're saying that zinc atom has a +2 charge. There's only 1 zinc on both sides. How many hydrogens? 2 and? Is that equation balanced?
Yes.
Yeah. Was it a redox?
No.
Hydrogen was at a +1 charge and it went to? 0. Did it change its charge?
Yes.
Or change its oxidation state? Yes, which means it was a redox reaction. Okay? And yes, it was reduced. Okay? So what's a big tip that we could go, oh, that's a redox reaction? We could look at determining the oxidation states all the way through. Okay? But we should have seen already that 2 of these elements were incredibly easy to determine their oxidation states for. H2 and Zn. What were their oxidation states? 0. Those species happen to be in their elemental state. Any element in its elemental state has what for an oxidation state? 0. Which then means I look at that element on the other side of the equation. Is it still in its elemental state? No? Redox. All I got to do is identify if it was a redox reaction, find an element in its elemental state. Did it change? That's a big red flag for a redox reaction. Okay? Take a look at this one. Okay, so a new equation to balance. Is it balanced?
Yeah.
How many tins? 1 and? How many irons? 1 and? 1. So is it balanced?
Yes.
Everyone want to say yes?
Yes.
No, it's not balanced. Why is it not balanced? What does charge represent? The balance of protons and electrons. Because we have the same number of, or the same atoms on both sides, okay, we have the protons balanced. Did we balance the electrons? What is the overall charge on the reactant side of the equation? It is a +5. What is the overall charge on the product side of the equation? +6. Is the balance of protons and electrons equivalent on both sides of the equation? No. What does that mean? It ain't balanced. Okay? Why does that now become tricky? Have we seen how to balance electrons? No. That's why it becomes tricky. We have an equation that looks trivial to balance. In actuality, it is not, because we have to balance something that we've decided was so unimportant that we don't actually show it. Okay? How could I balance the charge on each side? It's a really easy way to do it. How do I make +6 equal to +5? +1 what? Electron. Okay, where should I place that 1 electron? Product side or reactant side? I heard reactant first, so let's add an electron. What happens to the charge now on the reactant side? It becomes +4. Did I get closer or further from balancing the charge? Further. So that was not a good place to place the electron. So where should we place it? On the other side. What happens if I place it to the other side? What is my new charge? +6 plus a -1 gives me +5. Well, now the equation's balanced, except what have I shown in my equation? An electron. And what do we say about electrons? They cannot exist in balanced equations. fully balanced equations. So this equation is invalid, and we must come up with a way to account for that improper balancing. How do we do that? Okay, there's a variety of methods, probably the simplest of which is what's known as the half reaction method, or at least I find the simplest of which is the half reaction. So instead of looking at the whole reduction and oxidation reaction, I will now only look at half of it. What's a good half to look at? Okay. The whole point is to balance reactants with products. So if I only look at the reactants, can I balance? No. If I only look at the products, can I balance? No. How about I look at iron 3 on the left-hand side and tin plus 4 on the right-hand side? Would that allow me to balance? You're saying no. Why not? Different elements. I can't balance out different elements. So what should I do? Look at each element on each side. Meaning, what I would be doing is splitting it up into a half reaction along these lines. What happened to iron plus 3 to go to iron plus 2? It gained electrons. Gain of electrons is reduction. What half reaction am I looking at? The reduction half reaction and the oxidation half reaction. So I'm splitting my overall equation into the two component pieces. One is reduction, one's oxidation. Split them out, balance them out. How do I balance these though? Because aren't they each individually balanced on their own? One iron, right? Charge isn't balanced. How do I balance the charge in that first equation? What could I do? What's that? If I change the coefficient, I make this a 2, what is going to happen? It's going to make a 2 over here, and I'm right back to where I started. So changing the coefficient doesn't work. It's kind of annoying because I just went through and said, we can't do this, you can't do this, you can't do this. You can't do this with a full equation. Do I have a full equation? No. What could I not do with a full equation? Change the number of electrons. I'm no longer a full equation, which means I can change the number of electrons. I can add electrons to the equation to balance it out. Where should I place electrons for that first equation? All right, the product side. So we place an electron over here. What's the charge now on the product side? +1. What's the charge on the reactant side? +3. Did I balance it? No. Did I get closer or further? Further. So did I put it on the right side? So I'll put it on the other side. What happens now? Now I get +2 as a charge on the reactant side and a +2 on the product side. Is my charge balanced? Yes. Beautiful. What do I do to the next one? I had 2 electrons, and I'll place them on the product side. Why did I go to the product side this time? We have 2 options. We just went through that kind of process of elimination on just adding them and just seeing what happened. We did the first equation right. Okay? Because it's reduction and oxidation, if I know the first one needed electrons, guess what the second one has to do? It has to spit them out. They have to be on the product side. Now I want to add these 2 equations together. What has to happen to the number of electrons? They must completely cancel. Do they completely cancel? No. This is the exact issue we just saw. We said, oh, we just add an electron in. Because if we add them up, what do we end up with? Come on. Oh, yeah. There it is. We end up with the exact equation that we just had. And I said, doesn't work because we have an electron. We aren't allowed to have electrons in our final equation. So what do we have to do? We're going to tweak our half reactions. We're going to tweak the half reactions and change the amount of times that the half reaction runs. The electrons must equal each other on both sides. How do I make 1 equal to 2? Times 2. So if I multiply that top equation, or that 1 in front of my electrons by 2, what do I have to do to every other part of the equation? Which then means, let's see, do I have that neat? Which then means when I go through to add it up, what happens? I have 2 electrons on the reactant and 2 electrons on the product. What can I do? Cancel those terms. The exact same way I would cancel the system 2 plus x equals 4 plus 2. What does x equal? 4, because what did I do? Subtracted 2 from both sides. X equals 4. As long as I do the same thing to both sides, I'm good. Okay? When I add up my equation now, what happens? 10 plus 2 plus 2 iron plus 3s, or to make 2 iron plus 2s, and 1 tin plus 4. The whole point was to make sure our equation is balanced. Is our equation now balanced? Do our atoms balance out on both sides? Yes. Does the charge? Because the charge is the one that threw us under the bus last time. I have a plus 2 here, I have a plus 3 here. But, bless you,
Multiply that by 2.
I have to multiply by 2 because there's 2 of them. So what is the charge now on the reactant side?
6. Or
I have a plus 2 and a
8.
plus 6, so the charge is
Plus 8.
plus 8. What happens on the product side? I have a 2 times plus 2 plus 4. I get plus 4 gives me
Plus 8.
plus 8. Does 8 equal 8?
Yeah.
How that thing? Congratulations, it's now balanced. How does it get asked on the test? What is the sum of the coefficients for the balanced equation of 10 plus 2 with that? Guaranteed one of the answers is 4. Because 4 is entirely wrong. 4 would be assuming you just looked at it and you only balanced the elements, you did not balance the charge. Your fully balanced equation, your sum of your coefficients would be what? 6. 1 tin plus 2 irons plus 2 irons plus 1 tin gives me a 6 for my coefficient. Excited about that?
No.
So, take a swing. Record that again. So there are the answers to those. Don't practice on those. You can practice those at home. So ta-da, there are the answers. Next one. Here you go. Do this one. Balancing practice. Okay? And the reason why I'm asking this one is note the exam question. The question will be how many electrons were transferred in the course of this reaction. Balance it out. We add our electrons onto the sides. The electrons would not cancel, so it's not balanced. Okay? We need to make sure those electrons equal each other. How can I make 3 equal to 2? Or 2 equal to 3, actually. Multiply by what? I'll multiply the bottom one by 3, and I'll multiply the top one by 2. So I end up with 2 aluminum. I'll end up with 6 electrons there. I'll end up with 6 electrons here, 3 copper, 3 copper. When I add them up, what happens? The electrons will cancel. I'll end up with 2 aluminum plus 3 copper plus 2 goes to 2 aluminum plus 3 copper. Is that because you got it, Nick?
Yeah.
Awesome. So, what's the exam answer? It didn't say the total of the coefficients. We had a new question here. How many electrons were transferred? Why is it not 12? Isn't 6 plus 6 12?
They're the same electrons. We just
They're the same electrons. The electrons ejected by the aluminum in the first equation, it ejected 6 electrons. Where did those 6 electrons go? They were absorbed by our copper plus 2. I'm not adding the total electrons all together because those 6 electrons are the exact same electron. So the answer is 6 electrons were transferred. What other answers show up? 2, 3, and 12. Okay?
Where do you get 6?
3 times 2. So if we look at our top equation, we ran that top equation twice. So our 3 electrons became 6. We ran the bottom or the bottom equation 3 times, so the 2 electrons in that became 6. So what we looked at is to balance it out and get our electrons to cancel, they needed to equal the most common, smallest common numeral between them. What is the smallest common number between 2 and 3? 6. So I need to make sure both equations use 6 electrons. How do I get the 3 to be 6? Multiply everything by 2. How do I get this 2 to equal 6? Multiply everything by 3. So it's how I establish those coefficients. Okay. And as much as I would love to really continue talking about this, which isn't really officially true, it makes up a relatively small portion of the exam, and I don't want to spend a whole lot more time on it. Okay. If you have questions, absolutely ask them after class, review the video, and make sure you nail it down. Okay. Absolutely do that. Please, please, please. Okay. I would also encourage you to talk to the tutors. The tutors go through and show something different and the textbook shows something way different. So if you think this is confusing, read the textbook. Because that just, if you think stuff goes over your head, I read that and was like, what language is this? But some people understand it. I just don't. So the tutors have something slightly different that can manipulate and get to the same answers. As long as you can get there, you're good. The big question to ask them if they help you with balancing a redox reaction, how many electrons were transferred? If they can't answer that question with their method sucks. Okay? At least answer that question. Okay? Hooray, double replacement reactions. No more redox. Okay? You are expected, however, to predict your double replacement reactions. Okay? So when we look at our double replacement, aqueous barium chloride reacts with, notice the reacts is in quotes because maybe it doesn't actually react. And I'm not giving you enough information to decide that yet. So aqueous barium chloride reacts with aqueous potassium chromate to produce what? Okay. I'll go through and write out that top one. I expect you to go through and write out the bottom one. Okay. Whoever gets there first wins. Mine is longer, so. I wish I had some Jeopardy music. Do 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 do. Oof, chromate? Who wrote this question? Is that right? That's chromate, isn't it? I think I'm right. I'm done. Did you win?
Yeah.
Okay, what do you guys have?
NaCl,
NaCl, AQ, plus
NO3 with the negative
Li, NO3. NO3 is a negative charge, so I like where you're going with that. What is Li?
That's negative.
A +1 charge. Our formula is correct. We should not be writing a negative charge anywhere near the upper right-hand corners. What phase was that? Aqueous. This went to produce? Na, NO3 plus Li, Cl. Is that all you guys got? Who's right, me or you?
Do we include aqueous at the end?
We didn't include phases in yours. I included phases in mine. Why'd you not include phases in yours? You didn't know them. Okay, guess what? You need to know them. The phases on those actually are aqueous. Which means, did we get a phase change? No. Which means, what was your answer actually? No reaction. All you had to do was like 3 things. I had to do 4 things and balance and all that. What the heck? You should do that better. What's going on? How did we know the phases on those? How did I know that I produced a solid and know that yours were all aqueous? Kind of. It must be because I know some magic rule set that you don't know because I haven't told you yet. That's true. That's exactly it. Okay? There's a rule set that you are required to be able to manipulate, known as the solubility rules. Okay? The solubility rules tell you, do you have a solid or do you have an aqueous solution? Okay? If it is insoluble, that means it does not dissolve, which means what phase do we have? A solid. Okay? If it is soluble, that means it does dissolve, which means we have an aqueous phase. Okay? If your phase does not change, that is no chemical reaction. Okay? That goes back to the differences or deciding if we had a chemical or physical change. Okay? I do, however, like that you guys predict the products. That was an awesome job. Good job. You went through, you found the common things, you swapped the common things, and we've got the answer. Okay? Let's take a closer look at mine, because mine was a little bit more difficult. Notice at the end I put in a 2 there. Why is that 2 a coefficient and not a subscript? Why is the 2 there at all? To balance it, because on the left-hand side, how many potassiums do I have? 2. So I need 2 potassiums over here. Why did I not write K2? I could have done K2Cl2 because it says Cl2 here. Why is the red now bad? So a couple things. It's excessive. Kind of works. For those of you on the other screen here that can't really see those. Saying that KCl versus this being K2 and Cl2. Why is the 2 next to the Cl? To balance the, careful, barium. Is the Cl with barium anymore? No. So I can't put the 2 there because it's not with barium, or at least not for that reason. So I will ignore the 2 for the moment. Why is there a 2 with the potassium? Or in the reactant side. Why is there a 2 with that potassium? To balance out the chromate. Chromate has a -2 charge, which means I need 2 potassiums. Is potassium with chromate anymore? No, which means that 2 cannot be there for that reason. Before I start evaluating this coefficient, what do I have to do? Balance the formula. What is the charge on potassium? What is the charge on chloride? -1. Is my formula potassium chloride as written now correct? Yes. Now that my formula is correct, now I can balance the equation. And in the process of balancing the equation, that's where that 2 then comes from as my coefficient. All those steps. Okay? So the extra layer then comes in with our solubility rules. To be able to do this prediction, oh man, I drew it all out. Okay? How do we decide that difference? That is our solubility rules. So here's our solubility rules taken from the textbook. Okay? So if we take a look for that first equation, I'm trying to decide if barium chromate is soluble or insoluble. How do I do so? Look at my rules, and I need to find barium or chromate. Where do you see chromate? Rule 7. What does Rule 7 say? Ionic compounds containing those ions are insoluble in water. See Rule 1 for exceptions. What is Rule 1? Alkali metals and ammonium ion. The alkali metals are all group 1. Where is barium? Not in group 1. So do I have an exception to rule 7?
No. So
No. So the rule is insoluble. Insoluble means the phase is solid. There's my phase information. Potassium chloride. I need to look for potassium or chloride. Which one do you find? I heard rule number 4.
Potassium's number 1.
Yep, we'll go back to that. Number 4 has the chloride. The rule is that ionic compounds containing those are generally soluble, which would mean aqueous, with the exceptions being silver, mercury, or lead. Is potassium silver, mercury, or lead? No, which means no exception. The rule follows that it's soluble. That means the phase is aqueous. Okay? As Jerry was pointing out here, we could have just as easily looked at rule number 1. Rule number 1 says alkali metals and ions and the ammonium ion are always soluble. What is potassium?
in kind of
An alkali metal, which means
a, it's soluble.
it's soluble. How many of these rules should you commit to memory?
I get all of them.
It's kind of a balance there between some and none, or none and all. Right? How many do I have committed to memory? 3. Which 3? 1, 2, 3. What is special about rules 1, 2, and 3 that is not special about all the others? They're short, but why are they short? There's no exceptions for rules 1, 2, and 3. I do not waste time memorizing anything that has exceptions. That's a waste of time because then I have to memorize the exception as well. Okay? So what I expect you to be able to do is be able to use your solubility rules. I will give you a condensed set of solubility rules for the exam. Okay? You should still memorize rules 1, 2, 3 because they show up very, very often. If you've got them memorized, you don't need to reference a solubility table. They're already there in your head, ready to run and use. And because there's never an exception, you don't have to worry about being wrong. You're always right. Okay? Is that all of the solubility rules? Not by a bloody long shot. Okay? There's like 30, 40, 50 solubility rules. Okay? Again, why bother to memorize if there's so many exceptions? You're really only responsible for those first 3. The rest, you just have to be able to interpret the chart given to you. Okay? I know you're typing. I will come back, I promise. Our neutralization reactions are just a fancy double replacement. We're using acids and bases. Our acids have hydrogen, the base has hydroxide. We form water and a salt. Okay? And we'll look at that equation. The last one I want to mention real quickly is combustion. Combustion is a reaction of any organic material, carbon and hydrogen, with oxygen. Those reactions will always produce carbon dioxide and water. Okay? Relatively straightforward and simple in that respect. Do I have an equation? Then I have an equation there. So come Thursday, what we will do is I will ask a quiz within the first 5 minutes. Balance that equation. I want the full equation balanced and ready to go. Second question on the quiz. Sure, why not? Predict the products and balance that equation. Okay? Product of sulfuric acid and potassium hydroxide. And before you ask, but I didn't write it all down. It's in the PowerPoint slides. They're online. Use them. Because it'll give you the answer to one of them.
All this stuff.